Well, good evening. It's so good to be back with you all again. Tonight we're going to be looking at Chapter 10, and this will be my last time in the box, so to speak. I'll be with everybody through the rest of the course, but this is the last presentation that I'll be doing. We're going to go through all of Chapter 10 this evening. All right, so we'll jump right into it. And as we always like to say, if anybody finds us online stumbling across our videos, please let us know that you're out there. That's an encouragement to Gary and I to know that you're out there. This particular chapter has got a lot of little tidbits in it. We cover propagation and related topics in the technician and general. This chapter will expand on some of those concepts and get into some niche topics, so to speak. And there's about, 45 pool questions from this chapter, so it's worth going through. 4 sections tonight, starting out with 4.1 on electromagnetic waves. And that, quite simply, is a field created when potential energy stored in an electric or magnetic field changes. Remember, we talked about fields when we were talking about inductors and capacitors. That relates to this. And when we change electric and magnetic fields, we create electromagnetic waves. And it's, can you hear me? The electrons in a wire, an antenna, are moved by traveling electric waves, creating a weak current. That would be your antenna. So we transmit, and then we disturb the electrons in a distant piece of wire, an antenna, and like magic, we can hear. So this picture is a little bit hard to see the way it's laid out, but I've got an animation that might be helpful. Here we're showing an electric field, magnetic field, and the direction of the wave is going this way. A couple of pool questions here. The direction of an electromagnetic field. An electromagnetic field travels at right angles to the electric and magnetic fields. So here's these fields, and here's the direction of the wave. The orientation of electromagnetic wave components, the component fields of an electromagnetic wave, are at right angles to each other. We see that here. And if this works, we'll show you an animation that will make it a little bit easier to see. I'm going to turn this off first. There we go. Yeah, so here you can see the B field is the magnetic, the E field is the electric field, and the direction of the wave is the X, or on the X-axis there. So this is a little bit easier to visualize than the still picture that we showed. You've all seen a pencil in a glass of water. The pencil appears to bend. The reason that happens is because there's a density difference between the water and the air, and we're going to see that this directly applies to much of what we're going to be talking about in this section. The speed of it now, okay, so here's light and a pencil. Talking about electromagnetic waves, radio waves, the speed depends upon the density of the medium it is traveling through. And there's different media that are involved with radio signals. Air, first of all. Then we've got the ionospheric layers, different electron densities in the different regions or layers in the ionosphere. Radio waves travel through space, and they travel through earth and soil. These are all media that have different speeds that the radio waves will travel through and cause bending. That bending appears to happen at the media boundaries. We see in our glass of water here, the media boundary is where it appears to change.
We can't see your laser pointer.
Thank you. Here we go, yeah. So here's air, here's water. Waves appear to bend at media boundaries, the speed change, refraction. And the degree of speed change, or the amount of bending, if you want to call it that, is the index of refraction as compared to a vacuum. This is just kind of all background to help the pool question make more sense. Speaking of which, the index of refraction determines the speed of an electromagnetic wave in a medium. Now you might recall from last week Gary's discussion about tuned stubs and antennas and the fact that the velocity factor of the cable comes into play. That is related to this principle directly. The speed of the RF is determined by the index of refraction. As we saw, the practical application that Gary shared with us, velocity factor of a coaxial cable. Now you might want to take some notes as we go through this tonight. I've got some very interesting links through this presentation, and if you were interested in learning more about refractive index, which you may not be, which is fine, you might want to note that that is on page 6, or on slide number 6. Polarization, we've touched on in past classes, and it refers to the orientation of the electric field with respect to Earth. The animation that we saw early on tonight showed the electric field going vertically and the magnetic field going horizontally. In that case, with the electric field going vertically, that would be vertical polarization. What about satellites? They're spinning in space. Spin stabilization is a term that helps satellites stay on course. But if their antennas are spinning, we're getting some kind of a weird effect here. Do we want to receive that satellite with a vertically polarized antenna or a horizontally polarized antenna? Well, we can use something called a circular polarized antenna. What does that mean? Circularly polarized electromagnetic waves are waves with rotating electric and magnetic fields. And you can visualize that here if the satellite is spinning as it's going through space. So we have to use some special techniques so that that won't be fading in and out on us as it spins. And right on to some questions. There's only 4 pool questions in this section. So you feel free to unmute and give us an answer. 3-second rule. In what direction does an electromagnetic wave travel?
Delta.
It is delta. It travels at a right angle to the electric and magnetic fields. How are the component fields of an electromagnetic wave oriented?
Charlie.
Yeah, just another variation on the same concept. What determines the speed of an electromagnetic wave through a medium?
Delta.
Index of refraction. And denser medium will cause the wave to slow down. What are circularly polarized electromagnetic waves? Bravo. See, I'm giving you easy ones so far, so hang in there. Waves with rotating electric and magnetic fields, correct.
Yay for easy.
Yay for easy. All right. None of the material in this section is terribly difficult, but the pool committee managed to find 45 questions to ask us, so we'll touch on all of them. So here's another one that you might want to write down, slide number 13. This video here, the NASA solar cycle video, is really, really excellent. I highly recommend that you look at that if you have an interest. And here's another link. It has a whole bunch of videos contained within it. It's only this one's only 3 minutes long, so it should be easy to do. Now this slide, there's a number of things that we can pick out of this. Here we've got the sun. We've got a continuous thermonuclear fusion reaction going on, self-contained based on the gravity within the sun. So it doesn't just explode and splatter all over the place. A couple of things we want to pick up on. We've got the solar wind marked here. So the sun is continually throwing off particles. I think Dave Kassler called that junk. It's continuously throwing off junk. That's also known as the solar wind. And the other thing I wanted to point out is the thing that says flare here. Every so often, flares will erupt from the sun. They come at us at the speed of light. It takes about 8 minutes to get from the sun to the earth at the speed of light. Solar wind particles, on the other hand, can take hours to days to get here, and they both affect propagation in different ways. Another term that you'll hear is Earth-facing disk. So when the sun is facing us, what we're looking at is the Earth-facing disk. The sun rotates approximately every 30 days on its axis. And it's really weird. The sun is a big ball, big mass of squishy gas. The equator is actually rotating at a different speed than the poles, which is kind of a weird concept. But on average, it's about 30 days. So as there might be flares going on over here, as they rotate off the Earth-facing disk and go around back behind the sun, they'll come back in about a month if they're still active. So we've got ultraviolet and X-rays, which make up the radiation that's coming to us from a solar flare, the speed of light. We talked about eruptions, the solar wind. Now let's consider, okay, with all of this going on the sun, let's consider what's happening where we are on the Earth. So here's a picture of the Earth, and there's a compass needle here. The Earth has a magnetic field. That's why we can use compasses to find our way out of the woods. An interesting side fact here, there is a true north and a geographic north. And you might not realize that when you're holding a magnetic compass in your hand, that it might not be pointing true north. A lot of compasses will have a declination adjustment on them if it's a higher end compass, so that you can make that adjustment. Not really important to what we're talking about, but just being aware that true magnetic north and geographic north is different. We also have what's called a magnetic equator on the Earth, which also does not follow the equator of the Earth exactly. I'll have a picture of that in a little bit. So the Earth and the sun both have a magnetic field. The sun is about 100 times stronger. And our field, the Earth's field, is called the magnetosphere. And we're going to see how the sun impacts the magnetosphere on the Earth. So you've all been in a shopping center, and you come to these signs that says, "You are here." Well, here we are on the Earth. And here's a picture of the magnetosphere. Notice how it's kind of bigger on one side than the other. That's because of the solar wind impacting us. We've got the North Pole and the South Pole of the Earth. That's going to be important, because the magnetic poles will focus some of the sun's energy. We're talking about particle energy, actual physical pieces of stuff, junk, and it will actually come into the Earth's magnetosphere in the regions of the poles. And there's a solar parameter that talks about that I'm going to touch on. So the effect of those charged particles, here we've got a bar magnet lined up with the Earth. And you've probably all seen in your past science classes a bar magnet and iron filings. We don't have iron filings coming in from the sun. The particles are much smaller, but that this is the same concept. So the law of magnets, okay? Opposites attract, south and north, and pull toward each other. And these, of course, will repel. So depending upon the orientation, the magnetic orientation of the particles coming in from the sun, we're going to have an attraction effect or a repulsion effect. The solar parameter that describes that is called B sub z, which we're going to get into in a little bit more detail. So the repulsion orientation works toward canceling the Earth's magnetic field and negatively affects propagation. We'll see that coming up. The solar parameter B sub z. Now we're going to talk about measuring solar data. Here we've got the sun, and here I mentioned B sub z, and you'll notice that this is where particles can come in at the poles of the Earth. Now, wouldn't it be nice if we had some way of predicting how solar effects were going to change propagation? Well, in the case of the solar wind, we actually do. There's some satellites out there that are on the other side of the Earth that pick up different angles from the sun, and we actually can get some warning for certain kinds of propagation effects. And we've got something called the A satellite, which measures solar wind, and there's a GEOS magnometer satellite. There are several of them that will sense some of these things and give us a little bit of advance warning. You've probably all seen this kind of a display before. You find it all over the internet. If you go to qrz.com, a lot of people on their QRZ pages have linked this resource on their page. This particular one is from April of 2019. That's when when we were at a minimum in the sunspot cycle. April 2019, solar flux, SFI 67, sunspot number 0. This is a very sad picture. And here's the sun, and you can see that there's pretty much nothing going on there. Propagation, working dx around the world, probably wouldn't be too great. Now here's a happier picture. This is from December of 2024. I'm going to show you the current picture as well. Solar flux, SFI 167. Actually, I copied that wrong. It's 161. Sunspot number 114. This is very happy. And notice how active the sun is. There's all of these things going on. These bright spots on the sun are what are known as sunspots. And the way they calculate the number, they don't really count every single spot. They count groups of spots to come up with this number. The author of this display is Paul Herman, N0NBH. We're going to have a little bit more from him coming up. And these index values are readily available to us. I'll tell you how I like to use them. There's 3 ways, I've listed 3 ways that you can get to this. First of all, from the QRZ homepage, there's always a display. Paul Herman has his own link there on QRZ, and this display or a variation of it will show up there. And then there's a website that's just full of good information. So I wanted to provide these links to you so you could easily get to it. So this is one way to give a little bit of a prediction of what propagation might be. Let me zero in on one spot here. HF conditions, it says, and then there's a day and a night, and it predicts good for 80 meters through 10 meters at night. During the day, you see a little bit different picture. So in addition to some of these numbers that I'll talk more about, you've got these plain English predictions that you can look at. Occasionally, something might look good here, but if you go to that band, it might sound like it's totally dead, but the band might be open. Some people like to call CQ on a dead band and are very surprised to have people from the other side of the world respond to them. So you really can't tell by just listening to the band. Another way that you can predict a band being open is just listen to the FT8 frequencies. FT8 is the most popular mode in all of ham radio, and if you get a lot of activity on the FT8 frequencies, which is just in the space of one sideband channel, 3 kilohertz, you'll know that the propagation is open to some place in the world. And if you have the capability of decoding FT8 with free software, you can tell where the propagation is open. So let's have a look here at a couple of things that I like to check. Every time I turn on my radio, I usually like to have take a look at this. I look at SFI, I look at the sunspot number. BZ can have an effect. And here's some general guidelines here. For solar flux, SFI over 150, that's wonderful, ideal propagation. In this particular case, April of 23, it was at 167. That's fabulous. Sunspot number is the other one. Over 150 is exceptional. 100 to 150 is ideal. So what do we have here? We're in real good shape. Now there's a lot of things on this chart, and there was a fella who was very frustrated because he couldn't figure out what all of these things meant and couldn't really find a guideline on the internet that explained it, VE2XIP. So his approach was to study this and put together a document that explains some of this. So I've given you a link to that document. If you're taking notes, it's on page or slide number 21. And then there's a fabulous resource from the author of this diagram, N0NBH. He's got a glossary that describes all of this. And there's a link on his glossary page for a PDF version, which you can actually download, and I think it's 2 pages. Very, very helpful in understanding some of this stuff.
And I just want to remind folks who are watching on YouTube, the link to the Dropbox folder is in the description box on the YouTube webpage for this video, and we'll be sending an email out tomorrow to everyone on our mailing list that'll also have that link, so you can find this data tomorrow.
Right, yeah. And all of the slides that Gary puts in his PDF of the presentation, all of these links will work. One of the things I always do when I'm preparing a presentation, especially if it's one that we've done in the past, is go and make sure that all of the links work. Sometimes they don't. So the PDF version of this glossary is very handy, and it's on this page, this link. So here's the current solar numbers. I took this shot yesterday. It's from the Paul Herman site. So there's an Android app called Ham Solar that I'll show you. I mentioned that I look at this just about every time I operate. Since it's on the home screen of my phone, it's very simple for me to look at. Doesn't necessarily prove that I'm going to have great contest performance or DX performance, but there is a definite correlation. So I enjoy seeing what the solar numbers are just about every time I turn on the radio. So there's 2 things I look at. SFI and sunspot numbers, we saw. And the K index, we'll be talking more about that. If it's less than 2, that's a really good sign. So I'm going to show you, I'm going to go over to the calculator cam, show you a picture of my phone. I just found this resource yesterday, so it's fresh. There's a lot of features that I didn't get into, but I want to show you the base data. Kind of hard to see here, but I've got something called Ham Solar. This is what it looks like. It's on the Play Store, Android Play Store or Google Play Store. It's free, and it has no advertising, which is awesome. So I'm going to touch it, and bang, up comes the data. And this is current within less than an hour. This is December 2nd. SFI 200, wow. Sunspot number 177, wow. That's awesome. Now the K index, we're going to talk a little bit more about that. I like to see that at 2 or less. So that's the geomagnetic disturbance that we're experiencing in the Earth's magnetosphere. And that causes the geomagnetic field to be unsettled. That's not real bad. When it's 0, 1, or 2, it's very stable. So this is something that I look at just about every time I turn on my radio. And it's free. There's probably an Apple version of this as well, because I'm not in the Apple world. Do you
I
have
just
it?
looked, it's not.
It's not, okay. There's probably the equivalent though. There's a lot of ham radio resource sites available. I know that you can probably get to this easily. And maybe you can share that, Gary, if you find one. BZ, we talked about a little bit. Measures the direction and strength of the interplanetary magnetic field. Bunch of big words there. Now here's the trick. When BZ goes negative, the solar wind strongly couples to the Earth's magnetosphere. And that turns out to be a bad thing. Think of BZ as a door that allows transferring of significant amounts of energy from the sun, from the solar wind, into the Earth's magnetosphere. The more negative it goes, the more energy that can be transferred. resulting in more geomagnetic activity. The range for BZ is from plus 50 to minus 50. If it's close to zero or just slightly negative, it probably won't be much of an impact. Okay, so the solar wind will add to the Earth's geomagnetic field and upper atmosphere. It's pulling that stuff in. And then in the context of the pool questions you need to know about, B sub Z represents the north-south strength of the interplanetary magnetic field, or IMF. So that's the orientation of the solar wind coming in our direction. If negative, it aligns north to south, like the Earth's magnetic field. This southward orientation increases the likelihood that charged particles from the sun will cause disturbed conditions. See, I misspelled that. So B sub Z being negative will disturb the magnetic conditions here and negatively affect propagation. More measurements. I touched on K. We talk about A and K in the general class as well. The K index, just to review, goes from 0 to 9. Higher values, increased disruption of the geomagnetic field. This is the short-term stability. The other related parameter is the A index. It's derived from K. It takes basically a 24-hour average. And the only one that I usually look at is the K index, because I want to know what it's doing right now. When I turn on my radio and I want to operate, I want to see what K is doing. A gives you a little historical perspective, but I haven't really found a practical use for that, other than just to see that maybe things were bad 12 hours ago or 24 hours ago, but now they might be really good. So K is what I look at. A rising A or K index indicates an increasing disruption of the geomagnetic field. For the way that I use it, I just look for a low K, and then my happiness light goes on. There's another index called the G index. It's derived from A and K. Geomagnetic storminess, 0 to 5. It's coming up again here in a second. Another parameter is 304A. The 304A solar parameter measures ultraviolet emissions at 304 angstroms correlated to the solar flux index. And 304 angstroms is actually a wavelength of light. It happens to fall into the extreme ultraviolet range. So you can tell a little bit what's going on with that ionizing radiation by looking at the 304A parameter. And I wanted to share that because there's a poll question. Solar flares, these can actually cause radio blackouts if they're severe enough. So they are rated A, B, C through X. The greatest solar flare intensity is class X. That's a bad one. The cause, and it's typically the cause of short-term radio blackouts. Solar flares are the cause of short-term radio blackouts. These can last from minutes to hours sometimes. It's kind of weird because there's been times when, now the worst possible time for this to happen is right before a contest. And I know somebody who's in the room with us tonight. Gary's going to talk to us about having an experience with one of these.
Well, yeah, I was getting ready to operate. I don't know what the contest was, and I had checked things out the day before, so I came in, fired up all the radios, and I could hear nothing. And I checked, are my connections still there? Yeah, they're still there. I made a transmission just to see, power output, yes. SWR, low, but still nothing. This is back before I had a smartphone, so I had no idea what was going on, but it was only later that I discovered that there'd been an entire radio blackout that had lasted for a number of hours, and Bad timing.
Yep.
And while I have the floor here, Space Weather Live is an app on the Apple Store. It's the one that I use. And I like this one because it will give me notifications if there is a solar flare, if there's a CME, if there's a radio blackout in real time. So just having it on the phone, then you get the notifications and you know what's going on. So you don't have to be in the dark like I was.
Yep. The app that I showed earlier just kind of gives you the solar numbers. This looks like it goes beyond that, and you probably don't know if that's available in the Play Store, but I'm going to look after a while, maybe during our break, see if it's there. Those are good resources to have. Because when Gary experienced this, you wonder if your antenna fell down. Okay,
Exactly.
That's how bad it gets. All right, so just review in your own mind the blue text here. Geomagnetic storms. G and geomagnetic kind of go together. They range from 0 through 5. And the space weather term G5 means an extreme geomagnetic storm. There's all kinds of parameters that are out there. There's just a few of them that are mentioned in the pool here, and we're trying to highlight those to help you out. This is a very interesting video. I'll play it for you. I think it's only about a minute. Click on it here. I got to turn off my laser first. Oh, it should work. So here we've got the sun. We've got some solar wind coming off of it. And there's something going to happen. Wait for it. Bam! There comes a solar flare right toward the Earth. Oh man, look at this. So it hits the Earth. Look what it does to the magnetosphere. It really disrupts it. That snapback, I believe, is called the bow shock. So that's what happens when we have a solar flare. And they come at us at the speed of light. It's a light effect. No warning. Sometimes we can see from where sunspots are, there's a probability of solar flares that was also listed on the resource that I showed you earlier. There's a probability of solar flares, and those come from active sunspot areas. Here it is again, solar wind. All of a sudden, blam, solar flare. Could be a very unhappy event if it's a severe one.
And right now we're on the downward slope of the 11-year sunspot cycle, and this is when these activities are most prevalent.
Yep. So before contests, people are wishing and hoping and maybe even praying that the solar conditions are going to be mild. I put together a list of references here and made sure that all of the links worked. The ARRL handbook is a very good resource. Frank Donovan, I don't know if you've ever heard of him, W3LPL, he's a big time contester. I've heard him live at Contest University, which happens during the Dayton Hamvention or a day or two before it. And Frank actually rewrote the propagation section of the ARRL handbook a year or two ago. I think the handbook version 100, which I think is a year or two old now, has got all of his revisions. So I got to meet him at Contest University, along with another celebrity that I'll be introducing in just a second. So that's a good resource. I'm a firm believer that every ham should probably at some point in time have a copy of the ARRL handbook. So it's just a wealth of information. Spaceweather.com, the Solar Dynamics Observatory, NOAA, of course, is huge in this area, NASA, two different NOAA references here. And then if you watch the Dave Kassler video, he showed a bunch of animations of something called gray line propagation, which we haven't come to yet tonight, but this is the resource that he drew that from, dxatlas.com. There's a lot of other tools out there as well. And this book is excellent. I have a copy. Here to There, Radio Wave Propagation, available from Amazon. I usually recommend Amazon because it's free shipping if you're a Prime member, and a lot of people are now. And they're usually equal or less cost than the ARRL Direct and free shipping. There's a Kindle version for $10. I mentioned that sometimes to look for activity on bands, is a band open someplace? I have these frequencies programmed into my radio, so I can very quickly, by turning a knob, go from 1.8, 160 meters all the way up to 6 meters. And if I hear significant activity on these FT8 frequencies, I know that the band is open to someplace. So that this can be a useful reference as well. Of course, we don't know where it's from unless you have the ability to decode FT8, but the software is free. So this will give you a clue as well. Just something that I use. Now, WX6 SWW. SWW stands for Space Weather Woman, okay? That's what she calls herself. To meet this Gove, I got to see her at Hamvention. And also she did a presentation during Contest University at Dayton, I think this past year. Just a brilliant scientist, PhD. So she has a solar forecast, and the most recent one is from November 29th, just a couple days ago. She has a YouTube channel, and there's a bunch of mini courses that talk about solar effects that she has there. Those are excellent. And this is her website. If this works for us, I'm going to play just a minute or two of her latest forecast. I'm going to get my... Here we go.
We're in a bit of a hurry up and wait mode this week when it comes to space weather. As we take a look at our Earth-facing disk, we have been getting some fast solar wind from this irregularly shaped coronal hole. Some people say this hole looks a little bit like the back end of a bunny. I can kind of see that. Here's the cottontail, right? And you got maybe an ear here and an ear right there. These kinds of things are going to end up being more common over the next maybe 6 months or so as these coronal holes end up kind of being confined to this mid-latitude region. The reason for that is because you can actually see all these closed field regions in here. This is part of the heliospheric current sheet, and it's kind of confining these coronal holes to be in this mid-latitude region where we've got what I call the mid-latitude shredder, where all of these active regions kind of pop up, and they pop up in the middle of these structures. Plus, we're getting kind of this peeling off of the coronal hole off in these directions this way, both away, up toward the poles like that, along that symmetry axis. This kind of activity is completely normal for this part of the declining phase of the solar cycle. So expect to see more of this. This one might even survive its far side passage, and we'll see it again here in about.
What she meant by the far side passage, that's when these sunspots rotate around the sun and then come back in about 30 days. I'm going to advance now to where she talks about ham radio propagation and prediction. Let's see, that's at about 10:30. This was from just 2 days ago.
Coronal hole that's rotating through the Earth strike zone and sending us that fast solar wind. So at high latitudes, you're definitely getting shows, and that will continue over the next few days. If you're at mid latitudes, though, only if you're dedicated and you can chase substorms should you bother. Now, amateur radio operators and emergency responders, well, right now things are quiet, but it's the calm before the storm because you've got the big regions that are going to be rotating back into Earth view. So expect that noise floor on the dayside radio bands to start rising in and around the weekend, and expect the risk for radio blackouts to go way up into next week. You're probably going to have to hunker down. So get those.
So that's the ham radio forecast coming up. So the early part of this week, which we're in right now, could be seeing some flares. So that's fascinating. You've probably watched the weather at home. You find out if it's going to rain or snow or whatever. But to see a weather forecast from the point of view of the sun and solar conditions, just fascinating. I love watching her forecasts. You can find them online. All right, get my cursor back where I want it. These screens are separated by about 10 feet here, so finding my cursor can sometimes be a challenge. So here's some resources. And right into some questions. Okay, so I'm trying to share some things along the way here that will help you in your ham radio operating, in addition to addressing the pool questions from the chapter. So, speaking of pool questions, what is the cause of short-term radio blackouts?
Delta.
Delta, solar flares. Which of the following indicates the greatest solar flare intensity?
Delta.
Yep, there is no class Z. Which of the following is the space weather term for an extreme geomagnetic storm?
Delta.
Yep, correct. Geomagnetic and G go together, the clue. What does the 304A solar parameter measure?
Bravo.
Okay, the 304A and angstroms go together. That makes this an easy one to get. What is indicated by a rising A index or K index?
Alpha.
Alpha, increasing disturbance of the geomagnetic field, which correlates to poor propagation. What does the value of B sub Z represent?
Charlie.
North-south strength of the interplanetary magnetic field. What orientation of BZ increases the likelihood that charged particles from the sun will cause disturbed conditions? Alpha, southward, negative B sub Z. And right on to HF propagation. That's our next section. This is probably the longest section. We'll be adding some material along the way here. So there's three ways a radio signal can get from hither to yon, as they say. We've got space wave. That's this one here, where we're going point to point. Receive antennas can see each other. Then we've got ground wave. Be expanding on that a little bit. This is showing it as a straight line. It's actually curved, but we'll see that in a minute. Then we've got skywave, where we're actually going up into the ionosphere and then coming back down again. These signals are refracted, come back down to Earth, or skip, another term for it. And there's a bunch of things we can derive from this diagram. Do I have a bigger version? No, that's something else. So here we've got the ionosphere up above the Earth. We've got an antenna here. Now ground wave, got to be a vertical antenna because that's the only way that ground wave can work. So we can hear signals from the tower out to about this point on the Earth, or we can go up into the ionosphere, get refracted down, and then come back down to Earth. And anybody over here could hear us. If we happen to shoot into the ionosphere at a shallower angle, steep angle, shallow angle, it's just like bouncing a ball off the bank and banking it on a pool table. The further up you go, it'll change the direction of the ball, send it out a little further. So we're hitting the ionosphere further out with a shallower angle, and it comes down over here. So these are called skywaves. Now something else to pick out of this diagram, we've got a signal via ground wave. So any place in here, we can probably talk to our friends. At this particular point, we can talk to people over here. But in between these points, there's no RF getting down to the surface of the Earth. This is called the skip zone, or dead zone, if you want to call it that. There are some weird propagation effects that can cause you to be able to hear things in the skip zone, but for the purpose of this diagram, we're hearing nothing in this space here. Another thing, signals that go up into the ionosphere are not laser beams, okay? They spread out, and this is probably, even though it's showing it coming down at a specific point here, this is probably, it might be 50, 100 miles. A good long, it's like a flashlight beam, the way the signal spreads out. So a couple of other things we can pick up here, some terms. Angle of incidence, okay, that's incidence into the ionosphere. Elevation, how high are we elevating our signal? Vertical beam angle is another term. These all kind of mean the same thing. So some of your antennas will have very specific beam angles, and you want one with a fairly shallow beam angle if you want to talk a long ways out. And I have kind of an interesting side story here relating to skip zone. For a long time, I couldn't get contact with anybody in Georgia. I live in South Carolina, and I was worked all states, and Georgia was one of the last states that I was able to get. So why in the world was that? Well, they were far enough away where ground wave wasn't getting me there, but the higher bands were skipping over them. So it took quite a long time before I could make contact with somebody in Georgia and get my Worked All States award. But that's just a practical example of what can happen with these effects. Here's another picture. Got ground wave, and we've got the sky wave. I didn't mention from the previous diagram, the wave can come down to the Earth and then bounce back up again in the ionosphere, come back down again. You can actually go all the way around the Earth. This is how you can make it to Australia, in New Zealand, from the United States. You're doing multiple hops. Talk a little bit more about ground wave. It's an effect that only happens with vertical antennas. The lower part of the radio wave loses energy because of currents induced in the ground, which are mostly absorbed. And again, we saw our refraction commentary that we had earlier. Signals go more slowly in the ground and they're absorbed. This slows the lower portion of the wave, causing the wave to tilt forward slightly, following the curvature of the Earth. We saw that in our picture. The maximum range of ground wave propagation decreases as the signal frequency increases. So that's an inverse relationship. So it might help you to remember this by realizing that on 10 meters, 28 megahertz, you'll only go a few miles. So 10 meters is terrible for ground wave. 80, 160, much better propagation using ground wave. Something I borrowed from Kastler here. This is miles here, and he drew the frequency bands in, and you'll see that the lowest distance that he shows here is 10 meters. Gets better and better as you go lower in frequency. So just flipping back to the way the pool is listed, the maximum range of ground wave propagation decreases as the signal frequency increases. Couple of points and reiterating the pool question text. Vertical polarization is supported by ground wave propagation. And you can think of AM broadcast stations. Here's a picture of one. AM broadcast stations use vertical antennas. They usually load the towers. And by feeding the different towers in different phases, they can direct the beam. And Gary was talking to us last week about directing beams. It's only effective on the lower bands, 160 and 80, some effect on 40. The maximum range of ground wave propagation decreases as the signal frequency increases. And what helps me to remember that is that 10 meters is terrible. At the other end of the HF bands, much better. Now, we talked about the ionosphere in some detail in the general class. So this is just a review. You probably all know this. As the sun, Mr. Sun comes out and warms the Earth, in the atmosphere, there's different regions. These are called layers or regions. Don't get hung up on the term because you see it both ways. The D region is the closest to the Earth, where the gas molecules in the atmosphere are the most dense. Then we've got E, F1 and F2. These all form during daylight hours. This diagram is severely not to scale. These are very, very close to the Earth, actually. Like we're talking about where the airlines fly is up in these upper regions. Not to scale. So here's another picture. I had to kind of laugh when I saw this one, because normally you're not using dish antennas when you're on HF, going up into the ionosphere. And but it does show what's going on. So we've got aircraft flying, jet aircraft in the upper levels of the ionosphere. That's the heights that we're talking about. And here we've got a direct connection between two, and of course ground wave isn't shown here. Something that's not in the pool, at least not anymore, is something called NVIS. Kessler talked about this. This is near vertical incident sky wave. Wanted to share this because it could be very practical for you in your ham radio work. The way it works, the rooftop with red on it is where we're transmitting from, and we're shooting signals almost straight up into the ionosphere, and then they're coming down again. You might think, well, that seems kind of silly. Why would anybody want to do that? Well, in Dave Kessler's part of the world, which is mountainous, you can't talk through the mountain, but you can get on the other side of the mountain by doing this. So this is a trick that hams use. They run an HF net in Colorado that it really depends upon near vertical incident skywave propagation. The military uses this as well. So that this is real and you can use it. Well, how could you take advantage of this? Well, most dipole antennas or horizontal antennas tend to, you want to be at least half a wavelength high in order to have decent distance, a low angle of incidence to the ionosphere. So what you do to optimize for near vertical incident skywave is you bring that antenna down. You can go as low as maybe 1/10 of a wavelength above ground to accent the cloud burner, that's a term, cloud burner effect of that antenna. It's kind of shooting straight up, warming the clouds, but it's also coming down close in. Then we got one person over here that says, oops, too far away. It didn't come down there. So low dipole works. Skywave propagation, that's where we're going up into the ionosphere. We saw this diagram before. Signals that travel into the ionosphere can be refracted by ionized gas in the ionosphere's E and F region, returning to distance, or Earth some distance away. Reiterating some of what we talked about. And it happens, the refraction occurs because the ionized gases slow down. The electron density in the different regions or layers cause those waves to bend. So this is the primary mode for doing long distance communications on the higher frequencies. There's some skip distances just here for reference. One hop for the F layer is about 2,500 miles. From here to California, South Carolina to California is about 2,000, for example. One hop, skip and a jump. No, one hop skip distance for the E layer is about 1,500 miles. Lowering a signal's transmitted elevation angle increases the distance covered by each hop. Now this is an easy one to get backwards, so let's look at this picture again. If we lower the elevation angle, that's this one here, this is a lower elevation angle than this one. So if we lower the signal's transmitted elevation angle, this increases the distance covered by the hop. So you got to think about that a little bit, because this is a real easy one to get backwards. There's some really freaky things that happen when signals go up into the ionosphere. So we might have a linearly polarized wave down here on planet Earth. We go up into the ionosphere, and what in the world is this stuff going on here? It splits into two different beams when it hits the ionosphere. Something called an extraordinary beam and an ordinary beam. Well, that's weird. What's even weirder is these can take off in different directions. I don't know if you've ever heard of one-way propagation, where you can hear somebody that's strong, but they can't hear you at all. Sometimes this explains that effect. Ordinary and extraordinary waves are independently propagating, they call them elliptically polarized waves created in the ionosphere. Another way that I like to think of it is if you got a horizontal antenna, somebody with a vertical antenna some distance away is probably going to hear some of what you're sending. Normally horizontal, if the polarization isn't right, isn't the same on both ends, you have a greatly diminished signal. But you can have a little bit of both once they split into these so-called elliptically polarized waves. Independently propagating, created in the ionosphere. Really freaky stuff that's going on. And this is geographically dependent as well. A friend of mine, Eric Nichols, one of my favorite authors, I've had an opportunity to talk to him at Hamfest several times. He commented, in Alaska, they don't know where to point their beams because it's so messed up in Alaska with these effects. You're not sure if you're really pointing where you need to point to achieve your signal. So that this varies at different points on the Earth as well. And as I said, these waves can take different paths through the ionosphere. There's another concept here called chordal hop. Chordal hop propagation is successive ionospheric refractions without an intermediate reflection from the ground. So here is what we would normally expect for standard hops or standard skip. But with chordal hop, the signal winds up getting stuck in one of these ionospheric layers and goes a long way before it comes back down to Earth. You don't see this very often, but it does happen. It was actually hams that discovered this effect. Hams have done an awful lot to advance the radio art over history. So hopefully with that explanation you can see that, that this makes some sense now. Successive ionospheric refractions, so it's staying up there in that ionospheric layer without an intermediate reflection from the ground.
And if you could choose, this is what you want, because you get the least amount of attenuation.
Yep. Fewer distance traveled because you're not going up and down. Correct. It's more efficient because the wave doesn't have to return to Earth as it does with normal skip. Less length of travel. It can travel a long distance before getting refracted back to Earth.
Maybe we should invent a chordal hop antenna.
Wouldn't that be nice? This is a fairly rare effect, so I don't know how we would do that. The effect of chordal hop is that signal experiences less loss compared to the multi-hop using Earth as a reflector. So this is kind of saying something similar in two different ways, but there's two different pool questions there, so I wanted you to see them both. So here's an enlarged picture of what we just saw, but I will point out another thing. There's something called sporadic E that we're going to talk about a little bit more. People really don't know what causes it, but there can be electron layers floating around at the E level. You notice what's happening here. We've got this sort of violet signal, comes down to the Earth, it goes up to the E layer, and then comes back down again. So it hops up to the F, to the ground, up to E, and then down. So it's 1F plus 1E. Somebody described it that way. This green dashed one goes to F, to the ground, to E, to the ground, back up to the F, and then back down again. So there's all different ways that a signal can propagate through the ionosphere. Now let's see this. I think we'll take a break at this point because we've been going for about an hour. And if I finish this section, we'd be going another half an hour. So at this point in time, we'll go ahead and take our break, and then we'll finish up with solar effects on HF propagation before we get to the final section on VHF and UHF propagation. So at this point, let's take 5 minutes and go enjoy something different than this. Get your mind off of it for a bit. See you soon. Okay, we're back. We're going to talk now about the solar effects on HF propagation. We've touched on these a little bit in our previous discussion this evening. Drill down into some specifics now. Polar paths are more likely to experience high levels of absorption when the A or K index is elevated. That absorption, of course, is due to those the solar wind impinging on the Earth and affecting our magnetosphere. So now the auroral oval, okay, this is just talking about coming in over the poles. And for us, we're mostly concerned with the North Pole. There aren't too many people that are worried about the South Pole because we live so far away from it. Signal paths through the auroral oval, or the poles, are likely to experience high levels of absorption when the A or K indices are elevated. Something to know. And then something related to solar flares. A sudden rise in background noise across a large portion of the radio spectrum is an indication that a coronal mass injection or a solar flare has occurred. A CME and a solar flare are similar in that they bombard us with high levels of ionizing radiation. Another interesting sidelight, this would only happen on the sun side of the Earth, because the side of the Earth that was in darkness wouldn't see this. And I think Gary commented last time we did this that an absence of signal could be perceived as an increase in noise, and we've actually seen that. So skywave and long path propagation. So here we've got the Earth, we've got the light side and the dark side. We've got some hop going around the world. Now the circumference of the Earth, if you were to stretch a string all the way around it, is about 25,000 miles. So halfway around the Earth would be 12,500. Let's save that for a second. So the long path, meaning that we're going to go all the way around the world with our signal, that distance would be 25,000 miles. But if the person that we're not trying to go all the way around the Earth, then we're going to be going part of that distance, depending upon where it is we want to talk to the person. I've got a better illustration of that coming up. So Tokyo to Pittsburgh is about 6,600 miles. Yet this beam heading, long path would be 18,381. Which is the difference in distance between the two. So we can shoot our signal in one direction, the longer distance, and get there. We can reverse our antenna 180 degrees and possibly make that contact from the other direction. Sometimes you can notice an echo on a signal. If you do notice an echo on the signal, you could try to turn your beam 180 degrees for long path. That actually happens. It takes about 1/7 of a second for a signal to go all the way around the world, but it only takes about 30 milliseconds for your ear to detect an echo. So this is something that happens. An echo on a received signal may be caused by receiving a signal by more than one path. In this case, going around the world one way or going around the world the other way. So here's our relative distance related to milliseconds. Go all the way around the Earth in about 150 milliseconds, but we can perceive a change or an echo at about 30 milliseconds. So that's why this works. Now there's something else, again, a little sidelight here. There's something called LDEs, long delayed echoes. Kind of a paranormal thing. Some people think it's aliens repeating back to us or something like that.
I'm not saying it's aliens.
Yeah, but it might be, I don't know. But for normal everyday operations, 1/7 of a second is the normal time that it should take. Some very weird stories about this. Now we'll talk about gray line a little bit. Gray line, here we've got the sun, and half of the world is in darkness. So on the day side of the sun, we're ionizing the ionosphere, and at night we're not. So the ionization that is occurring on the sun side will slowly fade away as the Earth rotates into darkness. And the gray line or gray region is that terminator between dark and light. So the day side has an ionized F2 layer. That's the highest layer. The night side is just coming into sunlight, has not had time to ionize and absorb the lower frequency RF. So we get the double benefit to lower frequency propagation. Happens at dawn and dusk. That's the best time to see this from your location. And for me, working Asia very early in the morning, I'm benefited by gray line. Now the window where this is effective might only be 20 or 30 minutes. So you got to be there and expecting it if you're trying to make a contact this way. So station A and station B, we're both in the gray line or gray region. Pretty good chance we might have propagation. Now Kessler showed some pictures, and this is all from a resource called DX Atlas. There's a tool there that can show where the gray line is. Now you might be wondering, we saw back here that it seemed to be a nice straight line, okay? Why is it like an upside down U here? Well, that's because this is called the Mercator projection of the Earth, the map. And it's difficult to take a spherical Earth and flatten it out on a piece of paper, which is what we're used to seeing here. That's why we get this funny shaped U thing. And you can adjust this program, DX Atlas, for any time of the day or any time of the year to give you a clue where the gray line is. Kessler's demo was really excellent. Some more facts to know. Long path propagation is most frequent on the 40 and 20 meter amateur bands. Long path. For paths over 6,000 miles or less, the short path is usually the best because the signal will be stronger. And long path is usually observed either along the gray line or over on the nighttime side of the Earth. And I didn't want to get away from this. You had a wonderful story, Gary, about a schedule that you tried to set up with somebody.
Well, yeah, this is back in the mid-1980s. I was a relatively new ham at the time, and after getting my license back, I was licensed first in the 1960s. Anyway, my friend Greg was going on a de-expedition for a contest down to Montserrat, and he was going to operate there from Victor Papa 8 Mike United. I even remember the call sign. And his home call is K8GL. He's up in Traverse City, Michigan right now in that area. Hi, Greg. Anyway, we had a schedule. We set up a schedule that I would call him from my house in Saginaw, Michigan, down to Montserrat. And I had a 4-element TET 43 beam. I think we were on 20 meters. So I pointed it short path toward Montserrat at the time, and I called on the frequency we had arranged. Nothing. And on a whim, I turned the antenna 180 degrees and called him. Boom! Came right back.
Yep. So in that case, the short path actually turned out to be the skip zone. And
Yeah,
again,
no propagation that way, but long path, yeah, no problem.
so that's tying some of these concepts together, I hope. This is practical and real stuff. So a path entirely in darkness is most likely to support long-distance propagation on 160. That's because the D layer has virtually evaporated on the dark side of the moon. It's the D layer that absorbs those low frequency signals on the sun side of the Earth. Right, which is what this says. So a couple of things to pick up on here. A little bit more on the physics of gray line. The cause, at twilight and sunrise, the D layer absorption is low, while the E layer and F layer propagation remains high. And here again are the layers D, E, F1, and F2. Another picture of the layers. or regions. What should be done? Okay, and then here's another variation on the theme. What should be done to continue a long distance contact when the MUF, maximum usable frequency, for that path decreases due to darkness? Well, we can try switching to a lower frequency HF band. Now, we spend a lot of time in the general discussion, general class, talking about MUF and LUF and those sorts of things, but just know that it's maximum usable frequency for that time of day. So what should be done to continue a long distance contact? So you're talking to somebody and it's getting weaker and weaker and weaker. The path decreases due to darkness, so try a lower frequency HF band. That's a way to do it. Talk about fading. Now, fading is something that is the bane of communications. We all struggle with this. And what the reason for it is that signals are going from the transmitter to the person we're talking to over different paths. We saw that we split when signals go up into the ionosphere. They split and can go in different directions, or they can be bouncing off mountains, who knows. And that causes fading. There's a couple of ways to fight that. And they're not in the pool, but it's practical to know this. If you've got a site that's some distance away, perhaps when the signal fades out here, it's still strong here. So if there's some way of getting that audio back to your station, that's one way to fight it. It's called space diversity. And then there's something called polarization diversity. Remember, we split into elliptically polarized waves when we go into the ionosphere. It's possible if you've got two receivers, like on my ICOM 7610, I've got two independent receivers. And if I had two antennas, one horizontally polarized and one vertically polarized, on one in each ear, you can actually hear this effect where the signal will be stronger in one ear and then get weak and then be stronger in the other ear. That's called polarization diversity. So I just wanted to introduce you to the concept and the reason that we have fading. Propagation prediction. Now, I had a demo that I did in the general class, and I gave you the link to it and told you where to go to, where I demonstrated a product called a VOCAP, Voice of America Coverage Analysis Program. That's something that Gary is very familiar with because they depended on this to get their shortwave signals into different parts of the world. Do you want to comment on that, Gary? Or
I didn't use it, but our folks in Washington used it to schedule to the relay stations what frequency you should be using, what antenna you should be using, and with some of our curtain antennas, they were steerable, so we could, in azimuth, move them left or right, or in elevation, move them up or down, and they would tell us all the parameters that we were to use. All of these decisions were based on this software.
Mm-hmm. There are a couple of pool questions related to this. There's many other tools available. And it's possible there's propagation reporting networks that can show CW and digital mode signals. That's one means to see where you're getting in the world. And then VOCAP we just mentioned. Now, this one is kind of interesting. There's something called the reverse beacon network that will pick up FT8 signals and CW signals. They are just listening. So if I call CQ test, for example, in my call sign, some of these networks will pick me up and then put the fact that they heard me and what signal level they heard me at on a database that can be accessed via the internet. These are called propagation reporting networks. And the reason that they only work with digital mode and CW is because we're not smart enough yet in the single sideband world to decode call signs. People are working on that.
PSK Reporter is the one that I use.
Yep, and I'll show a picture of that coming up here in a minute too. So we've got these tools that can be used for finding out where propagation is. You can use it to compare different antennas as well. Then VOCAP we mentioned, Voice of America. And here's a picture of VOCAP online. You put in all kinds of parameters, your location, your signal strength, or your transmit power, your antenna type, and it will tell you, you can bring up a a picture that will show you which bands you're most likely to make that path. And again, go and look at that demo here if you're interested in seeing this in action. Here's PSK Reporter. I actually tried to get an image this afternoon, but for some reason my FT8 software wasn't working. So I'll use this one from a couple years ago. I was on 10 meters, FT8, calling CQ, and then by going to PSK Reporter, here's the link, then putting in my call sign, it told me where I was being received throughout the entire world. That is really cool. So that's another tool that you can use. And then I mentioned the reverse beacon network, which is usually used on CW, another tool. So this was about 5 minutes on the air. There's over 7,000 listening stations all over the world, and these are the ones that heard me. So a bunch of them in Europe, one in Africa, all over South America. So that's impressive what your signal is doing, how it's getting out. Some questions. How does the maximum range of ground wave propagation change when the signal frequency is increased? Charlie, yep. Good. And the 10 meters being terrible is how I like to remember that. What type of polarization is supported by ground wave propagation?
Bravo.
Alpha.
It's alpha.
No, alpha.
That's vertical.
Alpha.
Yes. Yeah, because half of the signal is directed into the ground. Good. Got it. What should be done to continue a long distance contact when the MUF for that path decreases due to darkness?
Bravo.
Switch to a lower frequency band. Correct. Which of the following paths is most likely to support long distance propagation on 160 meters?
Delta.
Delta, a path entirely in darkness because the D layer has evaporated, not absorbing the signals. What effect does lowering a signal's transmitted elevation angle, remember our picture here, we're lowering a transmitted signal's elevation angle, have on ionospheric HF skip propagation?
Charlie.
Charlie, you got it. It's an easy one to miss. What is the effect of chordal hop propagation? Alpha, the signal experiences less loss compared to multi-hop using Earth as a reflector. What is chordal hop propagation?
Bravo.
This is Bravo, successive ionospheric refractions without an intermediate reflection from the ground. The signal gets stuck up there in one of the ionization layers. What are extraordinary and ordinary waves?
Bravo.
It is Bravo, independently propagating elliptically polarized waves created in the ionosphere. What type of data is reported by amateur radio propagation reporting networks?
Delta.
45 minutes.
Delta, digital.
Thank you.
Yeah, somebody's
You
got
got your
some-
phone.
Yeah,
Okay.
somebody's
Okay,
got their
fine.
phone on and is being picked up. So, all right. So it was what type of data is reported by amateur radio propagation reporting networks? It's digital mode,
Delta.
and yep. What does vocap software model?
Charlie.
HF propagation. What?
Charlie.
Correct. Which of the following signal paths is most likely to experience high levels of absorption when the A or K index is elevated?
Bravo.
Through the auroral oval or over the poles. Which of the following is indicated by a sudden rise in radio background noise across a large portion of the radio spectrum?
Charlie. Bravo.
It is Bravo. Okay. I like it when a couple of people get them wrong because you'll never forget it when you get to that one again. So it's a coronal mass injection or solar flare has occurred. No shame in getting them wrong. On which of the following amateur bands is long path propagation most frequent?
Bravo.
Bravo, 40 meters and 20 meters. Long path. All right, then we'll get into our last section, And almost half the pool questions, believe it or not, in this chapter are in this section. So we've got a lot of really, really easy ones. And some very weird modes of propagation. Notice this says VHF and UHF microwave propagation. Everything we've talked about up till now has pretty much been HF. Now we're going to move up this frequency spectrum and see some unique forms of propagation that are primarily in the upper frequencies. The first concept is a radio horizon. And this concept just says that it's possible to see a signal a little bit beyond line of sight. So you would think if we're transmitting here, we can get down to the Earth, but we're still line of sight when we get over to here. But hams observed, again, ham radio to the rescue, or actually early radar operators observed that they could see beyond line of sight because of the bending of the signal due to the curvature of the Earth. So VHF, UHF radio is the furthest radio waves will travel directly via space wave propagation. That's point to point. And the downward bending is due to the density variations in the atmosphere. Causes the radio horizon to be a little further than the geographic horizon. It's about 15%. The radio horizon is about 15% greater than the geographic horizon. Okay, that wasn't so bad. Now this was introduced, ground gain and Fresnel zones were introduced in this version of the extra pool. So this is the second time that we've been through this. And I did quite a bit of research to try to figure out how to explain this, because it's something that a normal ham would never think about. The first concept is ground gain. It's an increase in signal strength from the ground reflections in the environment of the antenna. So this has to do with signals taking more than one path. If we go from point A to point B directly, we have a certain signal strength. If there's another path from point A to some object and then to the receive site, that's something that we're used to considering as multipath. Now that can be constructive or deconstructive. What that means is the signal might be improved, coming at you from two different directions, or it could be partially canceled. In ground gain, the improved side of that, increase in signal strength from the ground reflections in the environment of the antenna. So constructive additions of two signals arriving at the same point. So a reflected signal may arrive from a different direction, different path length. To the extent they reinforce each other, they add. And to the extent that they conflict with each other, cancel each other, it will hurt the signal strength. So it specifically considers the effect of ground reflections compared with the line of sight signal. And this is more prominent at 50 megahertz and up. So this is one concept of improving signal strength due to constructive addition. And then something called Fresnel zones. There's some really, really good information here. I like this link, zytrax.info. I love it when somebody tries to explain something technical using some humor. And this author does that. So if you want more information, I gave you the link there. So it's normally thought of in terms of radio link design. So here we've got a transmitter and a receiver. They can see each other. Well, that should be fine, right? Well, maybe not. A line of sight can be affected if there's something in the path. This is something called a Fresnel zone. It's an area in which if an object infringes into that zone, there's going to be some reflections from that object that will decrease the signal strength on the receive side. So this is quite often something that's taken into consideration when people are designing microwave paths. They do a site survey, they look at the transmit antenna, the receive site, and see if there's any obstacles that are within this Fresnel zone, which would decrease the signal strength. So they'd have to either raise the antennas or try to figure out how to get this object out of the way. If somebody built a building between the two areas, maybe you've got to tear the building down. That might not be advisable. Normally thought of in terms of radio link design. It's an elliptical area surrounding the direct path of the signal. Objects that get into the Fresnel zone, like this nasty object here, you probably can't read this, but it says nasty obstacle must be more than 60% from the center line in order for it not to affect this. Objects get into the Fresnel zone can reflect out of phase signals, which can cancel part of the signal at the receiver, even if there's a direct line of sight between them. In the Earth, if you've got a path that's miles long, the Earth can, because of the curvature of the Earth, infringe into that Fresnel zone. So how do you fix it? You either raise the antennas so that the zone clears the obstruction, or raise the frequency, because the Fresnel zones tend to become smaller at higher frequencies. Just one pool question for this aspect. The smallest first Fresnel zone will be the highest frequency band, and in our pool question, it's the 5.8 gigahertz band. So several links here if you want to learn more, but the pool question is pretty simple. All of that for that one, that one question. Tropospheric. Now this is interesting. It's an effect that often happens on VHF or even microwave. Now normally when the Earth is heated, the Earth gets hot, and then we've got cool air and then cold air as we go up in the atmosphere. But particularly over bodies of water, sometimes there can be an inversion of air temperature, cold air, warm air, and cold air. This temperature inversion causes a ducting effect or enables a ducting effect. Weather conditions that create a sharp transition between air layers, ducts, in the troposphere can allow VHF radio waves to follow the curvature of the Earth. And this is a mind blower for hundreds or thousands of miles, like a waveguide or duct. Now, when you've got you've got a pair of portable handheld 2-meter radios, you might get a couple miles, right? Well, what about going a couple hundred miles? This does actually happen sometimes because of this effect. So the propagation duct goes into this inversion. We got warm, we've got a warm, and then cool in the middle, so that forms a duct that can propagate that signal. Just another picture of it here. Now microwave is fascinating. We're getting up into the gigahertz range now. Atmospheric temperature inversion can cause a path for microwave as well. We were talking about VHF just now. So here's our temperature inversion thing. We've got bodies of water, and here we've got some raindrops. Tropospheric propagation of microwave signals often occurs along warm and cold fronts. And we were talking about bodies of water, but warm and cold fronts can cause this inversion as well, weather fronts, in forming over large bodies of water. I think we mentioned atmospheric ducts capable of propagating microwave signals often form over large bodies of water. And again, a mind blower, microwave signals can actually go 100 to 300 miles when they're propagated through a tropospheric duct. So it's real stuff. Probably talk from Texas to Florida over the Gulf of America, for example. Microwave propagation via rain scatter. The rain must be within the radio range of both stations. Of course, the wavelength of microwave signals is very short, so raindrops can actually be big enough to refract or reflect signals. Weird stuff here. We mentioned sporadic E earlier. It's still relatively unknown what causes this, but it's clouds of electrons that form in the E layer. Bounces signals off smaller clouds of unusually ionized atmospheric gas in the lower E region. Occasionally allows long-distance communication. And if you think 6 meters as being the place that you can normally see this, most commonly falls in the 28 to 150 megahertz range. And you can go fairly long distances. And this would be coming down. Remember we saw the skip happening like this, for example? Well, sporadic E can cause signals to come down in the skip zone. That might be how I talk to Georgia, for example. We don't really know. When is this happening? Well, sporadic E propagation is most likely to occur around the solstices, especially the summer solstice, June 21st. Now, something kind of magic happens in June. Like we've got field day and we've got VHF contests in that part of the calendar. It's most likely to occur between sunrise and sunset. Just a couple of points on sporadic E here. Just an expanded version of what we saw here. Now the Earth tilts during the seasons. We can see a progression. December, September, June, March. Actually, I'm going backwards there. But so the seasonal impact, okay, the sporadic E is best around the solstices, especially summer, when VHF contests are scheduled. Sure, that's not a coincidence. Another one, there's a secret weapon here that Gary and I use in DX contests, and we're going to talk about, called trans-equatorial propagation. It's a form of F-layer ionospheric propagation. Tends to occur on 6 meters and up, but it also can happen on HF. Now here's an Earth, and here's these funny little lines showing their trans-equatorial paths. TE propagation is most likely to occur between points separated by 2,000 miles to 3,000 miles over a path perpendicular to the geomagnetic equator. Okay, well, a couple years ago, I was tuning. I'd like to tune on bands when they're dead, when the sunspot, when we're in a low part of the sunspot cycle. And I noticed on 10 meters, I was hearing stations in Brazil. Well, that's weird. It was early afternoon, and I must have made 10 contacts or so. They were all FT8 contacts. Everyone was in Brazil. Well, that's really weird. I didn't understand anything about trans-equatorial propagation at that time, but the distance between South Carolina and Brazil is in this range. So the secret sauce, or the secret weapon that Gary and I both like to use during a DX contest in the afternoon, if you point your antenna south from South Carolina towards South America, you can have lots and lots of contacts in South America.
Yeah, I count on it.
Yeah, you count on it, right, right. So you take advantage of that. This is also something that was discovered by hams in the 40s, actually. The approximate maximum range for trans-equatorial propagation is 5,000 miles. 2,000 to 3,000, max 5,000. The time of day most likely to occur is in the afternoon or early evening. Not sure why it works, but it does. So we've got Greenville being about 2,400 miles from the equator, another similar distance into South America. Here's a picture. Now, I mentioned before that the magnetic equator isn't the same as the real equator, you want to call it that, of the Earth. So here am I in South Carolina, and here's Brazil, and you know the numbers just happen to work out. The red line is me. Another form of oddball propagation is auroral propagation, caused by the interaction in the E layer of charged particles from the sun within the Earth's magnetic field. Remember I said the poles would allow the energy from the sun to come in to the Earth's magnetosphere. Severe geomagnetic storms are most likely to result in auroral propagation. So when the conditions are disturbed, you might have a chance. And Gary last year shared a story about actually making a contact this way. Do you remember that, Gary?
I made my first ever auroral contact. I've talked about them in the classes and demonstrated in the technician class what it sounds like for single sideband. But I'd never worked one. But the weird, aurora was coming down toward South Carolina and Georgia, and so pointing a 6-meter antenna to the north, I was able to bounce my signal off of the aurora and have it come back down into a station in, I think it was Indiana.
Okay.
And he was pointed north going and coming back to me. It was freaky sounding, but I did it.
Mm-hmm. Yep. And CW is what a lot of people use there. That's a little bit easier than sideband. You can get propagation up to 1,400 miles. What band were you on, Gary?
6 meters.
6 meters, okay. So it was a VHF. Now we have the visible aurora when we get these charged particles coming into the Earth, and here's a picture of aurora. About a week or so ago, we had a fairly severe magnetic storm, and we were able to see the northern lights all the way into Georgia and South Carolina, which is rare. It's the same effect. Of course, we're not bouncing radio signals off the light, but it's that same effect of those charged particles coming in to the Earth's magnetosphere. And CW is the best emission mode for auroral propagation because it's so fuzzy and shaky. Gary was successful on sideband, but most people consider CW the best way to communicate when you're there. And the trick is you've got to be pointed north from the contiguous 48 states, United States. Channel pointed north will take maximum advantage. Here's a picture of northern lights. NOAA's got a whole bunch of really nice pictures of northern lights. Very beautiful. And here's how you do it. You point your antennas north toward the pole into the auroral zones, if you want to call it that. Moving on, something that I've wanted to try, but I haven't done it yet. Meteor scatter communications. Now here's another mind blower. Millions of meteoroids enter Earth's atmosphere daily. Now these can be the size of a dust mote or a piece of sand. They're small, but when they enter the atmosphere, they burn up. And when that happens, they create a linear ionized region behind them. So when a meteor strikes the Earth's atmosphere, a linear ionized region is formed in the E layer of the ionosphere. Well, that isn't going to last very long because that thing's going to burn up right away. So what tricks can we use to be able to bounce signals off those meteor trails? We'll come to that in a minute. The frequency range most suited for meteor scatter is between 28 megahertz and 148. Think of 6 meters. And now that I finally have a 6-meter antenna, I want to try this. I just haven't gotten around to it yet. Now MSK 144, part of the WSJTX family, is a digital mode designed for meteor scatter communications. Now how are we going to do this? Well, time transmission, MSK 144, 15-second time transmission sequences with stations alternating based on locations. So I might be sending out a CQ on 6 meters using this mode, MSK 144, and that path is gone by the time somebody has heard me and tries to respond. But they can respond and they might come back on another meteor trail. that actually can happen. So short transmissions with rapidly repeated call signs and signal reports, again, this mode takes advantage of that. In the good old days, I've never done this, but I know hams used to send very high-speed CW. They'd record CW and speed it up on a tape recorder and then slow it down on the other end and take advantage of those very brief opportunities. So here we are, we've got an ionized trail from a meteoroid. Transmit and receive and be up to 1,200 miles. Amazing. Here's some more pictures. The transmitter, receiver, something's bouncing off a meteor trail. Of course, this is wildly not to scale. It'd be something very tiny up there. And here's something that looks like an EME array, Earth, Moon, Earth, something, but in this case it's pointed up toward a meteor. There are certain times of the year that predictable meteor showers. Here's dates and the name of these meteor showers. So somebody that's chasing this kind of thing can concentrate on these dates. Now, moon bounce used to be very, very difficult to do, but it's more practical now with some of the modern modes, WSJTX modes. Moon bounce or Earth, Moon, Earth. There's certain times when it's easier to talk to the moon. That's when it's closer to us. Here's the Earth, here's the moon. It's kind of an elliptical orbit, but notice it's off-centered. So at some points in the moon's travel, it's further away. That's called the apogee. Some cases it's closer. That's called the perigee. How do you keep those two apart? Well, I've got a kind of a mental trick. Perigee sounds a little bit like a periscope. A periscope, stick it up above the water and you can see a distant ship that looks closer. So that was a trick that was helpful to me. Apogee, you can think of away or apart, the longer distance. And here's a link that talks about lunar orbit. Now, EME is not easy. So first of all, the moon, remember we talked about the circumference of the Earth, and from one side of the Earth to the other was about 12,000 miles. Well, the Earth, or the moon, is 225,000 miles away. But that's not the half of it, okay? The problem with trying to do Earth, Moon, Earth is there aren't any hams on the moon, okay? So you've got to double that distance. You've got to go this distance and then all the way back again if you're going to make a contact. So the beam width here, just a very tiny amount of your signal, like half a degree, is going to be hitting the moon at all. And fortunately, the moon has a rough surface. If it was a perfect sphere, you'd probably never be able to bounce anything off the moon because it'd be such a tiny, tiny amount that could come back. So everything that misses the moon winds up being lost shadow, or lost signal rather. There's something called libration fading, and there is a poll question about that. Now the Earth is kind of, it's rough, okay? So we've got a wave front coming in from our signal on the Earth toward the moon, but because the Earth is a fairly rough surface, there's a relatively large area that it can reflect off. But at the same time, the moon is kind of rocking back and forth. That's called libration, or libration fading in terms of the signal strength. Moon has an irregular surface, and this causes multipath, rapid flutter, deep fading in peaks. And the thing to know here, libration fading of an EME signal is characterized by a fluttery, irregular fading. Two links here, how to use moon bounce, and there's a Wikipedia article. So this is the wave front hitting the moon. This is the weird looking wave front coming back because of those irregularities. Now, fortunately, our friend Joe Taylor created some modes that make moon bounce a lot easier. It used to be you had to have super cooled preamps and dish antennas and the highest amount of power you could possibly generate in order to even have a chance at moon bounce. This software has brought it into the realm where average Joe ham can actually do moon bounce. I've never tried it, but a number of my friends have. So this all started back in 2001. The JT65, which a lot of you might have used on HF, was really designed for moon bounce. Q65 is the current version for EME, and it uses time sync transmissions. In other words, you transmit for a certain number of seconds, and then the other person transmits on the other time slot. Now, of course, both stations have got to see the moon at the same time, so they'd have to be within 12,500 miles of one another in order to both have a path to the moon. VHF and UHF. Approximate maximum separation measured along the surface of the Earth between two stations is about 12,000 miles. Moon has to be visible by both stations. And hams can actually achieve DXEC, 100 confirmed contacts on 2 meters using EME, or moon bounce. Still, low noise receiving is essential because the signals are so weak. Q65 is the digital mode commonly used for EME today. And then here's now JT65 was the mode that was first used for moon bounce. A characteristic, and there's still a poll question on it, a characteristic of the JT65 mode is the ability to decode signals which are very low signal to noise. We use time synchronous transmissions. I transmit for a certain number of seconds, then you transmit. That's how Q65 works. Libration fading is characterized by a fluttery, irregular fading. And when scheduling EME contacts, the least path loss occurs when the moon is at perigee, closest to the Earth. Gives a 2 dB advantage. Now notice there's 1, 2, 3, 4, there's 5 different questions on EME. You're only going to get one, if any, but hopefully you've absorbed that as we've talked through it. And on to some questions. So we're approaching the end of our class. How does VHF-UHF radio horizon compare to the geographic horizon?
Alpha.
It is alpha. You can talk about 15% further than the line of sight. What does the term ground gain mean?
Delta.
Delta, an increase in the signal strength from ground reflections in the environment of the antenna. And what frequency band has the smallest first Fresnel zone?
Alpha.
Yeah, but it's the highest one there. It's 5.8 gigahertz. Atmospheric ducts capable of propagating microwave signals often form over what geographic feature?
Charlie.
Charlie, large bodies of water. I told you that a lot of these are really easy, and there's lots of them, so we like lots of easy questions. What is a typical range for tropospheric duct propagation of microwave signals?
Bravo.
It is Bravo, 100 to 300 miles. At what time of year is sporadic E propagation most likely to occur?
Alpha.
Alpha.
Alpha, yep, around field day, around the solstices, especially in the summer solstice. Easy to say word there. At what time of day is sporadic E propagation most likely to occur?
Delta.
Delta, between sunrise and sunset, the sunny part of the day. What is trans-equatorial propagation? When is, or where is it most likely to occur? I'll get it right one of these times.
Alpha.
Alpha, between points separated by 2,000 to 3,000 miles over a path perpendicular to the geomagnetic equator. What is the approximate maximum range for TE? Charlie, that's the 5,000 miles. What time of day is trans-equatorial propagation most likely to occur?
Charlie.
Afternoon or early evening. What is most likely to result in auroral propagation? Charlie, disturbed conditions, severe geomagnetic storms. Which of these emission modes is best for auroral propagation?
Alpha.
Alpha, CW. Gary was successful on sideband. Which of the following digital modes is designed for meteor scatter communications?
Bravo.
Bravo, MSK 144. When a meteor strikes the Earth's atmosphere, a linear ionized region is formed at what region of the ionosphere?
Alpha.
Right, exactly. Which of the following frequency ranges is most suited for meteor scatter communications?
Charlie.
That is Charlie. Somebody's got a radio on in the background. You might want to mute
TV.
yourself. Okay. You might,
TV, way too loud.
yeah. Turn that off or mute it. Or maybe you can see who it is, Gary, and mute him. Which of the following digital modes is designed for EME communications?
Delta.
Delta.
Q65 Delta. Yep. What is the characteristic of the JT65 mode?
Bravo.
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 Yeah, see, I'm keeping my promise. Easy questions here. Bravo. Decode signals with very low signal-to-noise ratio. Which of the following is a method for establishing EME contacts? Uh-oh, did I stump you?
Alpha.
It is alpha. Time
Alpha.
synchronous transmissions alternating between stations. What is the approximate maximum separation measured along the surface of the Earth between two stations communicating by EME?
Alpha.
Delta.
It is delta from
Yeah.
one
Yeah, you got to see the moon.
one
Gotta
yeah,
be
you
able
got
to
to be
see
able
the
to
moon.
see the
Gotta
moon
see the moon.
at opposite ends of the Earth, 12,000 miles. What characterizes libration fading of an EME signal?
Bravo.
Bravo. Fluttery, irregular fading. Correct. When scheduling EME contacts, which of these conditions will generally result in the least path loss?
Alpha.
Alpha.
Yep, when the moon is at perigee, closest to the Earth. Now, I've got just two bonus slides here that you might find interesting. One is the concept of antipode. And here we've got a person, I don't know if you can see him, his butt's kind of up in the air, he's got his head in the ground, and if he goes all the way through the Earth, where's he going to come up on the other side? Well, in this case, it's right next to Australia. And this site has got some humor built into it. It says, oops, do you know how to swim?
Now, is this proof the Earth is flat?
Maybe it is. I don't know. But why is this useful? Well, it's kind of interesting to know that the furthest you could talk from your location to someplace else in the world, it's actually a little bit east of Australia for me here in South Carolina. So that's the concept of an antipode, opposite end of the Earth. And you can do this from this link if you're interested. So what country would be your furthest? And so New Zealand and Australia are happy things for me when I find them. Then there's something called an ionosonde. Very briefly, it's a radar. It's an upward firing radar that sweeps frequencies and then looks at the signal coming back. It's an article on Wikipedia. Let me show you what an ionogram looks like. So here we're sweeping frequencies from, looks like about 1.8 megahertz up through, in this case, about 6.5 megahertz. So we're shooting a signal straight up, and then the reflection that we're getting back will define, in this case, the E layer, F2. This is the ordinary and extraordinary waves that we saw. Here's this is just a general concept. Here's an actual picture of an ionogram. And notice that we have the same general features, but we got this stuff way up here. What in the world is that? Well, this signal from our up-firing radar comes back down to the Earth and then bounces and goes back up again. So we get these ghost reflections to bounce back to the Earth. A lot more to that. I'd point you toward the article about that, but that's how they can characterize E and F performance. And then finally, a book that I picked up at Dayton Hamvention back in 2018, another Eric Nichols book. It talks a lot about propagation. This is focused on receiving antennas, but it's something that I'd recommend if you want to learn a little bit more information relating to propagation and antenna design. And that is all we have for tonight. I ended 1 minute early. So what are we going to do next week, Gary?
Well, next week we're going to be in the last chapter of the book. It's maybe the most important chapter in the book, safety. We're going to try to keep you safe. I'm going to try to convince you that ham radio is an adventure. And then after we finish that in the first half of class, we'll take a 50-question multiple choice test And you can do better than the instructor. I can preview that now, that I might not have gotten them all right, but you can do better.
Yeah. Very good. So I think
Any comments or questions before we go?
Thank you.
yeah, we
You
covered,
betcha.
we
I
covered
want
a
to
lot
thank the
tonight.
international viewers. We had viewers on YouTube from Germany and from England, the live stream, and from Switzerland in our Zoom classroom. So, yay!
Yeah. We're going to have to go for DXCC in our class.
That's right. Until next week, then. 73, y'all.
Yep. Good
Thanks,
night.
guys. Appreciate it. Have a good one.
Yep.